We have two concepts today that are connected through energy. We're revisiting first collisions. Okay, so now we're in the position to think about the energy associated with collisions and the energy changes. So two kinds of collisions that I want you thinking about. One, elastic. So in an elastic collision, the kinetic energy is conserved. So we add it up before the collision, we add it up right after the collision, and the total energy hasn't changed. Now it may have been moved around, converted between objects, but nevertheless, it'll be conserved. The other kind of collision is everything else. Okay? So in elastic collisions, the kinetic energy is not conserved. So we can't say anything about it. It's not one of these conservation laws that we can use to solve problems. Okay? So here's an example. This is a one-dimensional collision. The key idea here is that with all collisions, momentum is conserved. That's that top equation on the left there. But in an elastic collision, the kinetic energy is also conserved. So we can use that again to help us solve problems. Now again, this is one dimension, but don't forget about those vector signs. We're gonna generally stay with one-dimensional motion because it's complicated enough. But just know that those are really the vectors, velocity, v1, v2. Now, I strongly encourage you not to memorize results here, okay? So, get comfortable with the basic concepts, that is the conservation laws, okay? But I don't want you memorizing all these special case results. So, one of those special case results is a specific kind of inelastic collision. Again, the kinetic energy is not conserved, but after they collide, they stick together. Okay. So again, the kinetic energy is never conserved. We can never say anything about the kinetic energy before and afterwards unless it's a special case where we measure it. Okay? But we get this kinetic energy that's lost because of the deformation. And in that deformation, you can imagine there are non-conservative forces doing work, producing thermal energy. So here we can apply momentum conservation, but that's really it. Now the second topic has to do with power. And when you think about power, I want you thinking about the rate of change of energy, or the rate at which work is done. Okay? How quickly we climb up the stairs. How quickly the tension force pulls the elevator upward. Okay? So again, there are a number of special cases here, but again, the key idea where you begin is that power is rate of energy transfer per unit time. And from that, we can build everything else. So don't waste your time memorizing a bunch of equations. I'll give you them all, okay? But you have to be conversant in their use, okay? So again, focus on some of the special cases. I think that there's some challenging problems to do. So take your time and come and chat with me as you begin to try to work through these problems.